Hey, welcome to today's video. I'm Prof. Omar. Today is the second in a series of 4 videos on the Putnam 2018 number A6 problem. And it's in collaboration with Professor Michael Penn, who has his own channel on YouTube. That's a wonderful channel that you should totally check out. So he's presented the first solution right over here, and I'm going to present the second solution on my channel. Then his solution, the third one, is going to be presented on my channel, and I'm going to present a fourth on his channel. So I'll be presenting the second solution and the fourth solution. And I want to say that this second solution is not something that I would come up with like during an exam or during a contest time. But it does illuminate a lot of interesting mathematics. The fourth solution that I'll present on his channel will actually have some interesting things, so you should totally check that out. And that's more of the style of something you might be able to come up with during an actual exam. All right, so let's talk about this problem. So the problem states that you have 4 points A, B, C, D, no 3 of which lie on a line, and they're in the plane. And you're given the information that the square of the lengths of each of the sides, the pairwise distances, is rational themselves. And then you want to prove that this quantity here, the ratio of the area of ABC to ABD, is itself a rational number. Okay, so let's start out by at least drawing the situation we have at hand. So we have something like the following, like 2 triangles of some sort. And then we have these vertices, A, B, C, D. And I'm going to label the edges as well because they'll be useful throughout the argument. I'm going to label them in a way so that they go in order of alphabetical order of the label of the vertices. So here we'll have an A, and then a B, and then C, and then D, and then E, and then F as the labels. All right. So the approach to this problem is going to use what's called Heron's formula. And that's a way to express the area of a triangle in terms of the side lengths of the triangle. And it looks something like this. So the area of ABC, for example, which has side lengths A, B, and D, is 1/4 the square root of this quantity right over here. And if you observe, this quantity is the sum of the side lengths times something that looks like the sum of the side lengths, like 3 different expressions like that, but where we change one of the variables from being positive to negative in each one of the corresponding product ends. We have the same thing here for the area of triangle ABD. Okay, so our goal is to show that the ratio of the areas here is going to be a rational number. Now, the issue with the ratio of these areas is that it's an expression involving square roots and like the division of them. So that's kind of a little bit annoying. So what we'll do instead is show that the area of triangle ABC times the area of triangle ABD is rational. Now, a question is, why is this enough? And another question is, why is this even a useful approach? Okay, so you notice first that this quantity here is this quantity, which I'll call star, divided by the square of the area of triangle ABD. Okay, now the square of ABD is a 16th times this entire product right over here. Now we can group this product in a clever way. We have A plus C plus E, and then the minus A plus C plus E we can rewrite as A minus C minus E and then pull the negative out. Okay, we can do a similar thing over here. We have here A plus C minus E, and then we can think of the next quantity as A minus C minus E. Okay, so then as a consequence, this quantity is negative 16 times A squared minus the quantity C plus E squared times A squared plus the quantity C minus E squared. Okay, so why am I doing all this stuff? So we get here then negative 16 negative 16 times a to the fourth, we have a minus of c plus e times c minus e is c squared minus e squared. So we have that squared. And then the term in the middle is the sum of these two multiplied by the a squared. And that sum is twice c squared plus e squared. So you notice this expression is here is represented in terms of the squares of a, c, and e. And so we're given that those numbers are rational. So this thing actually is rational, right? And so that means that this quantity here is rational. So this is rational precisely when this thing here is rational. So we'll work with this instead. And a reason so that justifies that we can work with this instead. But why work with this? Well, looking at the product of these things, we'll have 1 over 16 times the square root of a bunch of stuff. It's the product of 8 trinomials in the variables that we have. And so working with just one big expression that's almost a polynomial, it's like the square root of a polynomial, will allow us to maybe get some traction. Okay, so let's see how. So what we'll do is, instead of actually working to try to prove this is rational, we're going to do something that's kind of really interesting. So again, our goal is to prove that this expression here is rational. What we'll do is look at its square. So a square gets rid of all those square roots. Okay, and by the same argument we had on the previous page, we know that this expression here can be written as a to the fourth minus 2a squared times c squared plus e squared, and then plus c squared minus e squared squared. And that's the same with this expression right over here, but in the different variables. So we'll have a to the fourth minus 2a squared times b squared plus d squared, plus b squared minus d squared, all squared. Okay, so we do notice that this expression here is rational. And the reason that's the case is because, again, a squared, b squared, c squared, d squared are all rational numbers, and e squared. Okay, but that's not enough to prove that this quantity here is rational, right? All that does is prove that this product of the squares is rational. So what we're going to do is find a way to augment this expression to make it a perfect square. So we're going to augment this to make it a perfect square as a polynomial in A. If we do that, then let's think about what happens. There's a way to change this expression so that it is a square as a polynomial in A. Then whatever is the square root of, that thing is going to be the product of the area of ABC and ABD. So if it happens to be an expression that is rational, then this quantity we want here is rational. But how do we actually augment this thing to make it a square? Well, we can add 0 in a way that's kind of clever. And this is where I think you have to sort of look way beyond what we typically do in a contest situation and think about an expression that's forced to be 0 in all of these variables, a, b, c, d, e, f. And there is one, and it uses something that we actually presented a few videos ago on this channel. Okay, so I've actually taken the time to take this expression and expand it fully as a polynomial in A, and it looks something like this. And again, our goal is to show that this thing is rational, and we're trying to augment this in some way to make it a perfect square. Okay, so here's the way we're going to do it. So I'm going to go back to this page right over here, and steal this picture and draw it again and use it for inspiration on a way to get an expression that has to be identically 0 that we can use. Okay. So the expression we're going to use is this lovely expression that tells us the volume of a tetrahedron given its side lengths. So we can think about this thing as actually being a tetrahedron with 0 volume. So if the volume of a tetrahedron is V, then there's this formula for the volume that says that the volume squared times 288 is the determinant of a certain 5 by 5 matrix. It's the matrix that looks like the following. You have zeros, a 0, and then 1s on the first row and first column, zeros along the main diagonal, and then the squares of these lengths in a certain prescribed way as the rest of the entries. So you notice this is a symmetric matrix. Okay, so this is the volume of, or the square of the volume of such a tetrahedron. Now this is an example of a tetrahedron here with volume 0. So we get that this thing here is identically 0 in our situation. Now this thing actually is a polynomial in A. We can expand it out to figure out what it is. Now it takes some work to do that. I'm not going to do the details here, but it gives us a way to augment this particular expression here by allowing us to add multiples of this polynomial here, whatever it is, to this expression that we have at the top to hopefully get some kind of perfect square that will allow us to prove that this thing here actually is rational. Okay, so I won't go through the steps of actually computing what this determinant is. I'll just take for granted. So I'm going to rewrite this expression that we have and then write down the determinant. So the determinant is going to look something like this expression here involving all of these terms. So what I've done is I've collected, you notice the determinant here has to be a polynomial in A of degree 4 because we only see an A squared and A squared here, the product of which is A to the 4th. Okay, and it turns out to be this expression right over here. I've done some rearranging of terms, so not only did I expand the determinant, which we know is identically 0 by the volume argument we mentioned, but each of the coefficients is going to have these expressions in terms of the other variables B, C, D, E, and F, and I've collected them in sort of clever ways. It's a kind of fun exercise for you to try to figure out how to do this. I've done it in this way because it sort of mimics what's happening in this expression right over here. So for example, I've clumped together this factor of b squared minus d squared and c squared minus e squared because I know that this is an expression that's right over here. Okay, so how can we go about using this to do what we're aiming to do? So we'll take a look at this expression. You notice it's a polynomial in A whose powers are all even. So if it's a perfect square, it's going to look something like A to the 4th plus some quantity times A squared, and then plus this square root of this thing right over here. So it's going to be a B squared minus D squared times C squared minus E squared for the last term. So that starts to give us some hints on how to go about trying to write this thing as a perfect square. Right, so the first thing that we get a hint about is by looking at comparing terms. Again, we're allowed to multiply this expression right over here by anything that we like, and we'll still have 0. So what types of things should we choose? Well, it might make sense to augment this in a way that doesn't mess up this term right over here. So it only contributes to these intermediate terms over here. The a to the 6th, a to the 4th, and a squared coefficient. So it would make sense to actually multiply all of these things by a squared, at least at first. So we'll have a squared, a to the 4th, and a to the 6th here, all being 0. Maybe I'll make this clearer by crossing them out and then writing them. So we'll have here a squared, a to the 4th, and a to the 6th. And again, this is still 0 because we've multiplied the entire expression, which was 0 to begin with, by a squared. Okay, so now it takes sort of some fiddling to play around and get a sense of what to do. We could compare either the a squared coefficients or the coefficients of a to the 4th. Okay, and if you play around with the a to the 4th coefficients, this one and this one, it'll give you a suggestion of what you ought to do. And the goal, again, is looking at what the expression, if this thing here was a perfect square, it would have to look like this. What would the a to the 4th coefficient have to look like? So the a to the 4th coefficient would have, so there's this function, I guess I'll call it h of b, c, d, e, f, sitting right over here. The a to the 4th coefficient will have a 2 times b squared minus d squared times c squared minus e squared, contributed from this factor here and this factor here twice, plus the square of whatever this mysterious function coefficient is beside a squared. Okay, so what we'd want to do is compare this expression to everything that's underlined here. You have like this whole thing right over here, and then this entire thing right over here. Okay, if you're trying to force something like a 2 times b squared c squared times c squared, b squared minus d squared times c squared minus e squared, you start to see that there's some contributions already. So you have something like the b squared minus d squared squared, the c squared minus e squared squared, and then you have this intermediate term right over here that when combined can do something for you. Okay, so the algebra ends up being quite messy here, but it turns out that it works out if you multiply this expression by -2. And you might ask, how did I come up with this -2 to begin with? I came up with it by trying to maneuver using exactly the principle that I'm showing right over here. The only reason I'm not getting into the details is it turns out to be quite a little bit messy. And if you do that and collect terms, the final result that you end up getting looks something like this. It's a to the 4th plus the quantity b squared plus c squared plus d squared plus e squared minus 2f squared a squared plus b squared minus d squared times c squared minus e squared squared. Okay, so this underlying thing here is the quantity whose square is precisely this thing that we want right over here. And so that tells us then, by looking inside of the squares, that 4 squared times the area of triangle ABC times the area of triangle ABD is rational, because the expression underlined right over here is represented in terms of the squares of all of the lengths of the triangle of the expression that we had over here on the previous page. And So this expression here is rational. And so that means that this thing is rational here. So we did reach our goal of establishing that this thing here is rational. And as a consequence, the ratio of these two is rational by the argument that we made way at the beginning. Okay, cool. So this is an interesting way to go about this problem, and it uses quite a bit of algebra that I've skipped because the algebra is actually quite intense, working with 8-degree polynomials and many, many, many variables. So I think the thing to get out of this, though, is sort of two things. One is that we can use this interesting formulation of the volume in a really interesting way to get some information about something that has to be identically zero in terms of the side lengths of a triangle, or side lengths of a quadrilateral, like the one that we have. And also this idea of if you have a polynomial that you're trying to show as a perfect square, try to find something that's zero to augment it by maneuver and then be able to do that. One thing I'll mention as a side note as a consequence of this, like independent of the actual problem we're working on, you see now that if you have a quadrilateral like this in the plane, then there's an identity between the side lengths that you get by setting this quantity equal to zero. In fact, that this expression here that we had originally on right over here is identically zero for such a quadrilateral. Okay, so interesting stuff. And in the next video, we'll have Prof. Penn actually have a different solution. And in the fourth video, I'll have a solution on his channel that is much more akin to the type of thing that would develop techniques for actually solving problems when you're actually doing problems on the contest itself. But I really like the ideas behind the solution. I wanted to present it to give you ideas that are sort of really out of the box. So I hope you enjoyed today's video. If you did, definitely click the like button. And if you want to see more videos like this, definitely subscribe to the channel.